Okay, so last time I was trying to explain the relationship between crystal operators and Knuth moves, right? So I got stuck on a proof there, and then when I went home again, it looked quite easy. So but somehow on the board it wasn't working out. So let's start there. So the thing I wanted to show was that I defined these crystal operators EI, Fi, and sigma I for I goes from 1 to n minus 1, and then I told you that so I'll take H to be one of these things. So I told you that if you look at H of W and you look at its Q star, then this is the same as the Q star of W. This was one fact. I only proved it in the case where n is 2, okay, when you have 2 letters in your alphabet. There the proof is much simpler. When you have more letters, the proof gets more complicated. Now the other thing I wanted to say was that suppose you have two words that are Knuth equivalent. So suppose I have W, which is Knuth equivalent to W prime. Then I claim that, let me state it a little more carefully, if HW is not equal to 0, then HW prime is also not equal to 0, and HW is congruent to HW prime. Right. So what we are saying is that we have these words, and then on the one hand you can find the PW or maybe P star W. This is the Robinson correspondence. It gives you two components. On the other hand, you get standard tableau. So Q star W. So maybe I should write it like this: P star, Q star. Here we get tab AN. Here we get standard tableau, and there will be the same shape on both sides, right? So it's not very clear here what's happening, but what I'm saying is that AN star to union over lambda, tab lambda AN, or maybe tab star lambda AN cross Q star, standard tableau of shape lambda. Okay, so this is the RS star correspondence. Okay, so what this is saying is that, and a coplactic class is defined as follows. It's a class of all words, say let's say CQ. So let's fix Q some standard tableau. Then CQ is a set of all words W in AN star such that Q star W is equal to some this fixed Q. Okay, and what we are saying is that if you apply a crystal operator, then you remain in the same coplactic class. The Q star doesn't change, right? Yeah. So this the motivation for defining the coplactic class was that if you take some W in CQ where Q has shape lambda, fix Q with shape lambda, then you get the Schur polynomial. So maybe I can write it like this: S of shape Q, the Schur polynomial of shape Q. So this is the whole motivation for doing this, but we are also going to think of it in terms of crystal operators. So this is what we want to show. So the all the action in this, it's enough to assume that W and W prime differ by a Knuth move. So let's take one of the Knuth moves. The other Knuth move, the proof will be similar. There's also a symmetry with respect to crystal operators and Schützen-Berger involution. So maybe that's a good exercise for the tutorial. Is Digjoy here? So yeah, so here's the question. So if I take EI and apply W, then this is F n minus I plus 1 W hash, or maybe I can put the hash here. This hash is, remember, the Schützen-Berger involution, which reverses the order of the alphabet and the order of the letters in each word. So and then we saw that it takes K1 to K2 and K2 to K1, this Schützen-Berger involution. So usually if you prove things for one of the Knuth moves, you can use Schützen-Berger involution to prove it for the other. Of course, not necessary, just an aside, but it may be something good to look at in the. It will give you a the more exercises you solve, the better feel you will get for these things. So here's the thing: we'll assume that W is equal to so let's assume that W is equal to U X Z Y W V, and W prime is equal to U Z X Y V, and I need to take X strictly less than Y less than or equal to Z. No, X less than or equal to Y strictly less than Z, I think. Okay, so now we are going to apply some Plactic operator here. So let's say we apply so which one takes so let's just recall the definition of the operators. So what does EI do? Where? N minus I plus 1. 1 goes to N, so N minus 1 plus 1, so that's N. N goes to 1. So N minus En. Oh, there may be something here. Yeah. Good catch. Yeah. So that's also part of the exercise. So yeah. So we had that little example, right, where you can actually see what's happening. You can take those words. We have the case where the shape is 2, 1 and you have 3 letters. We worked that out ad nauseum. So you can just apply the Schützen-Berger involution to that entire example and you'll get the same things, but the arrows will be, I mean, it's a symmetry of that diagram, in fact. So with which reverses the arrows. Yeah. So what are the words for where all? Yeah. So yesterday I asked which are the words for which all the FIs vanish. So they are the Schützen-Berger involutes of Yamanouchi words, but you can also try to characterize them in other ways. So yeah. So now the thing is, when you apply a crystal operator, so let's say I'm going to apply, so what does EI do? What is it? I raised to R plus 1, J raised to S minus 1, and Fi takes I raised to R, J raised to S to I raised to R minus 1, J raised to S plus 1. So in some sense Fi is moving you towards No, EI is moving you towards Yamanouchi words, right? So all the EIs will vanish on a Yamanouchi word. So you can never remember which is which. So let's here, for example, apply. Let's try to increase, change an I to a J. So let's apply Fi. So I want to look at FIW and FIW prime. Now what happens when you apply Fi is that there's some place in the word where you're going to change an I to a J. Okay, and if that place happens before the Knuth, outside the segment, inside U or inside V, then it doesn't matter, because in W prime also it happened in the same place, and so this Knuth move remains just the same Knuth move. There's nothing really happening. So the cases to worry about are when the I that is changed to a J is one of these three letters, right? So we have three cases. So we have U, I, Z, Y, V, and this is U, Z, I, Y, V, or we have the case U, X, Z, I, V. So this is I is Y, and here we have U, Z, X, I, V, and then we have, maybe I'll write this on this side. And the last case is we have U, X, I, Y, V, and U, I, X, Y, V. So what we want to show is that in each of these cases, these two are Knuth equivalent, right? So of course we have these kind of inequalities as well. So it could be that in you know, these are not, these same inequalities do not hold after changing my I to a J. Sorry, this is W and this is W prime, and now I need to apply F. So this I know are Knuth equivalent. Now let's apply Fi. So this will become U, J, Z, Y, V, where J is I plus 1. And here I will get U, Z, J, Y, V. Here I will get U, X, Z, J, V, and here I will get U, Z, X, J, V, and here I will get U, X, J, Y, V, and here I will get U, J, X, Y, V. So these are the different things that Fi can do depending on which of these three letters was I. It's also possible that two of these letters were equal to I, X and Y were both equal to I. So you could also have U, X and Y, right? So X and Y. I, Z, I, V is congruent to U, Z, I, V, and then here you would have U, J, Z, J, V is equal to U, Z, J, J, V. So all these different cases that you have to worry about. Let's just go through some of them. So let me start with say pick at random. Let's look at this third case here. So I want to know whether these are Knuth equivalent or not. So I have this. So what do I know here? I know that. So this comes from here. So I know that X is less than or equal to I is strictly less than Z, right? So let's just look at this case. Okay, so I'm looking at this case. So that comes from here. So I have U, X, I, Y and U, I. So what I know is that X is less than or equal to I, which is less than or equal to Z. Now I'm replacing this I by a J, right? So what could happen is that I could have X less than or equal to J, Now j is I plus 1. Huh? I have x less than. Sorry, this is x. Oh, this is. Yeah. No, I'm just asking if this is true or not. So this may not be true, right? This is z equals I. Yeah, this is z equal to I. So x less than. Okay, so this one is really easy. So I'm asking whether I still have this, and surely it's true, right? Because j is I plus 1. So this one is easy. Just because when I replace I by j, this inequality remains true. Yeah. So let's look at a case where this may not be true. So let's look at the case where this is I and this is z here, and the only issue is that z is equal to j. Then we no longer have this, right? This is not true. So which case am I looking at? I am looking at I equals y. So it's this case, xz. So basically this is only a problem. So if z is greater than j, then it's okay. So the only case I am looking at is this one where z is equal to j. So I have u x j I v, and I want to know if this is the same as no. So I have u x j I v, and and it's congruent to u x j x I v. But look at this. This is a j I, right? And when we were doing our freezing process, we actually cut out all these things. So this cannot happen. I mean, it can never happen that that this z was equal to j. Okay, and all these proofs actually basically involve tricks like that. Except perhaps maybe this last one. So here think about this last one. This is interesting. So. Oh yeah, that's right. So here, what do? I replace the last I, right? So the thing that can happen here is this, if at all. So remember that when we are doing our thing, we remove the last unfrozen a, unless of course z is j. Unless z is j, in which case you would have u I j j v, and here you would have u j I j v. So yeah. So then then this would become u j j j v. What? So anyway, you have to do all these different cases. I won't do all of them, but there are little arguments like this. It's not particularly difficult. So what is the second point we have is that if two things two things are congruent and you apply a Knuth move, then they remain congruent. In particular, if you take corollary of 2, suppose I take W and I take its P star W, okay, and then I apply H to this. So this will be, so this H preserves these dual tableau. So this will again be a dual tableau, and it will be Knuth equivalent to HW. So these crystal operators commute with the P star operator. Right, so what am I saying? So let me find some space here. Yeah, so P star HW is congruent to HW, and P star W congruent to W. And what does this say? H of P star W. So 2 implies H of P star W is congruent to HW, which means that H of P star W is equal to P star HW. But we know that there is a unique, by the RS star curve, so there is a unique column word of a tableau in each Plactic class. So these must be equal. So congruence implies equality for tableau or dual tableau. Yeah, I'm using that. So here's one way to see this. So maybe I didn't do this. So suppose you have let's just take a tableau. And let's take its row word. And let's look at its Q star. So I just have to keep track of the shapes as I insert these things from right to left. So first I'll insert the 4, then the 4 will get pushed down by the 2, and then the 1, and then the 1, right? And then what will happen next is I'll have another 4 that will bump out this 4 and it will come to rest here. So I'll get 5. No, yeah, the second one will bump out the 1, so that's the 5. Sorry, what am I doing? 4, yeah, let's just do it slowly. 2, 4, and then 1, and then 1, and then 4. Let's see, what am I doing? So and then I bring in the 3. Yeah, so then the 3 bumps out this 4. No, the 4 is here, right? Oh, is it? So 6. Wait a sec. This it can't even be like this, right? I'm doing it wrong. Let me just do it carefully. So first I put the 4, so I get 1, 2, 4, right? And I get here 1, 2, 3. Now I have this 1, so I put it in and it bumps out this 1, so I get 4. And then I put in this 4, So it bumps this 4, which comes over here, right? And then I put in this 3. So this 3 bumps this 4, which then bumps this 4. And then I get 6, and then this one more 3. So one more 3 bumps this 3, and then that bumps this 4, and so I get this. So what I wanted to say is that I'll get this tableau, but that doesn't seem to be happening. So the 3. Okay, let me not get caught up in this. We'll think about it later. So the point is, if you have, okay, so yeah, the shapes will be the same from the RS, but yeah. Yeah, so from the RS you can see it, right? So if you take a crystal operator applied here, then the Q remains the same, but yeah, so I wanted to say that the Q remains the same, and these tableaux should all have the same Q. So that's what I was trying to say, and so I wanted to show that directly, but yeah, so from the RS what you know is that all these tableaux will have the same Q. So if you apply the crystal operator, they'll have the same Q, and so it follows that it will remain a tableau because the Q will be the same. So anyway, so this is so these crystal operators commute with insertion and dual insertion. So that's a corollary, and now we recall. So we have, on the one hand, we have coplactic classes, and on the other hand we have crystals. So let me define the crystal now. So crystals are, you start with any word W. So I would say the connected component or a connected component of AN star endowed with the colored directed graph structure. I should explain what this means, coming from crystal operators. EI and FI. Maybe we'll just say Fi, 1 to n minus 1. So we've seen an example of this. So you just start with any word W, and you apply to it. So you look at all the words AN star in AN star, and then you just apply to them all the FIs. Okay, so this gives so you, of course sometimes Fi may be 0, in that case you don't do anything, but if Fi is non-zero, draw an edge from W to FIW of color I. So, this is the graph structure on AN star where W is joined by a directed edge with label I if to FIW. So, this is the graph structure, and then you think of it as an undirected graph and look at all the connected components. Well, as connected graph also. Okay. So, it's all the things which are joined by a series of edges. Okay. So, what have we seen here? So what we have seen here is that if you apply a crystal operator, then the Q star does not change. So, what does this mean in terms of the relation? So, we want to show that the coplactic classes are the crystals, right? Correct. So, what we are saying is that every crystal is contained in a coplactic class, or every coplactic class is a union of crystals. By this one, because if you apply a crystal operator, the Q star does not change, so you remain in the same coplactic class. But in fact, the theorem is that every coplactic class is a single crystal. For this, we will use the fact that every coplactic class contains a unique Yamanouchi word, and every crystal also contains a unique Yamanouchi word. No, contains at least one Yamanouchi word. Well, we do not know that a priori. So, I described to you last time an algorithm where you can start with any word and you can keep applying the operators Fi till you reach Ei, till you reach a Yamanouchi word, right. If it is not Yamanouchi, that means you can apply at least one of the Eis and then you apply it, and then if it is not Yamanouchi, you can apply at least one of the Eis and you apply it, and this process must stop at some point, because you know there's the weights, what happens to the weights each time you apply Ei is that they become more and more dominant, and with this, so that process must stop in finitely many steps and you will eventually reach a word which is Yamanouchi. So, the proof is that every W in A star, for every W in AN star, there exists I1, I2, Ij, Is belongs to 1 to n minus 1, such that Ei1, Ei2, Eis of W is Yamanouchi. So, every crystal contains a Yamanouchi word. But we saw last time that every coplactic class contains a unique Yamanouchi word. Class contains a unique Yamanouchi word. So that Yamanouchi word we actually explicitly constructed. Given a standard tableau, that Yamanouchi word is the word which you read the Yamanouchi word and you start putting the elements 1, 2, 3, 4 and so on in the row number that you read. So we did that correspondence between Yamanouchi words and standard tableau. No, so for a Yamanouchi word, you will have the standard tableau will be so yeah. So here's maybe let me remind you. So suppose you have a Yamanouchi word. Let's take something like this. So it's easier to write Yamanouchi words if you start from the left. So 1, 2, 1, 3, 2. Yeah, 1. So let's look at this Yamanouchi word, and let's just try to look at its column insertion. So P star. So first in goes the 1, and then the 2 comes down below it, and then the 1. So what does the 1 do? It bumps out this 1 over here, and then this 3 comes down below it. And then what does the 2 do? It bumps this 2 to the next column. And then this 1, what does it do? It bumps this 1 over here, and which in turn bumps over here. So what's happening is, at any stage you have more 1s, you have fewer 2s and you have fewer 3s. And now I am trying to insert something. Let's say at this stage I'm probably somewhere here, right? Here. So now I'm trying to, suppose I try to insert a 1 here, it will come and rest in this first row. If I try to insert a 2 here, it will come and rest in this row. The only problem that could happen is if I already had a 2 here and I try to insert it here, then it would come here. But then that wouldn't be a Yamanouchi word, because at that stage you would have more 2s than 1s. So the P star of a Yamanouchi word is what is called superstandard. There is only one such tableau for each shape lambda. So every crystal, every coplactic class contains a unique Yamanouchi word. Yeah, we are using RS. So if you had two different crystals inside the same coplactic class, but there's only one Yamanouchi word, right? So that's not possible. Each crystal is contains the Yamanouchi word, and so it's the entire coplactic class. So that's thing, but in fact we can say more. So as sets, coplactic classes are crystals, but then there is a particular coplactic class which consists of all the tableau. Yeah. Yeah. EI is the inverse of Fi if it's defined. So if you have a chain of EIs, then you can go in the opposite direction and get the Fis. The coplactic class of the sorry, I need to look at this picture. So here you've got the superstandard, and if you apply Yeah. So this will be this super standard is the dual insertion tableau of every Yamanouchi word. So the Yamanouchi words are precisely one Plactic class, one Knuth equivalence, yeah, are all Knuth equivalent, huh? Yeah. Yeah. Yes. So if you take this super standard word and you look at its coplactic class, that will contain all the tableau. So there's the super standard tableau. Let's call this Y. It's Yamanouchi lambda, in this case 3310. So this is the Yamanouchi word 322211. So this is the super standard tableau, and it's a tableau. So if I apply no, it's so coplactic classes will have a unique dominant word and all the other words will be derived from it by the crystal operations. Its coplactic class will consist of one model for the representation V lambda, namely the semi-standard Young tableau. And there is one model for each Yamanouchi word. Okay, so if you can think of these models as these are the same as indexed by Yamanouchi words. This was Robinson's original conception of this thing. So what I want to claim is now the isomorphism theorem, that any two crystals, remember crystals are endowed with this color directed graph structure containing Yamanouchi word of the same weight containing a Yamanouchi word, containing Yamanouchi words of the same weight. So each crystal contains a unique Yamanouchi word, right? So you look at those Yamanouchi words. Are isomorphic. So the proof basically comes from this theorem. We'll show that both the crystals are isomorphic to the crystal consisting of coming from the Yamanouchi word of the super standard, the super standard Yamanouchi word. So suppose I have here Y lambda. This is some Yamanouchi word of shape lambda, and I have here Y0 lambda. So this is the insertion tableau of Y lambda, the column insertion tableau of Y lambda. And now I can apply these operators. What do you call them? E or F? F1, F2, F3, whenever they are applicable. So if I apply some operator here, I know I can also apply it here, right? That's what this theorem says, that if I can apply a crystal operator on this side, then I can also apply it on that side. And then what I have is that, so this is the insertion tableau of this. So these will be the insertion tableaus of these things. So this would be f1 y lambda, f2 y lambda, f3 y lambda, and this is p of y lambda, and these will be p of f1 y lambda, and so on. And so the isomorphism will be given by just taking W goes to PW. Okay, and what we have seen here is this thing says that it is actually an isomorphism, that if you apply a crystal operator and then take P, then it's the same. So they are all isomorphic to the crystal consisting of column words of semi-standard Young tableau, and therefore they are all isomorphic. So that's the isomorphism. It's much simpler in this case because you have this notion of Knuth equivalence and you have Robinson's correspondence, which we used repeatedly to do this. P star maybe, yeah. We can do it with P. I just did it P star because that's how Robinson first did, and it seems closer to the way it works with path models. Okay, so that's the isomorphism theorem, and it's a very powerful theorem. It lets you immediately now understand the Littlewood-Richardson rule. So that was already proved here, yeah, but maybe this argument can also be used. So I think you saw some examples in the tutorial, right? And I also did that usual example of 2-1 with 3 letters, where we had 2 of these crystals. And one was semi-standard tableau and the other was some column words, and then okay, so that's the isomorphism theorem. Now let's come to the Littlewood-Richardson rule. So the starting point for the Littlewood-Richardson rule is this formula here, which again comes from the Robinson correspondence. That, well, okay, you have to start somewhere. So we started with the definition of Schur function as a weighted sum of semi-standard Young tableau, right? That's called Kostka's definition of the Schur function. So there are like many definitions of the Schur function. Probably the oldest one is the Cauchy bialternant formula. Then there are Jacobi's and Trudy's formula, which are determinants. Then there is Schur's characterization as the character of an irreducible representation of GLN. And then there's Kostka's, which is a purely combinatorial thing. So did you do the symmetry of the Schur function, Digjoy? Okay. So that has a nice proof using crystal operators if you start with Kostka's definition. So now what we want to do is we have S mu, S nu, and we want to understand this in terms of lambda, C lambda, mu nu, S lambda. And we can work with n variables where n is fixed, and everything will then work with the alphabet an and so on. But usually what we do is we just take n to be very large. when these things will stabilize. But let's just see what the proof gives us in fact. So what we know is that if you are working in n variables, then this kind of thing holds, where I'm looking at words in this coplactic class of Q. Of course, here I need to specify that they are words in AN. So let's just write out the left hand side. So we can also index this if we want by a Yamanouchi word, right? So we can take all the words in the crystal containing a Yamanouchi word. So let me just rewrite this again. S lambda is equal to sum of crystal of any Yamanouchi word of shape lambda V of W. So what I need to say is this: B y lambda is the connected component of y lambda, where this is any Yamanouchi word of weight lambda. So I just call that yam lambda. So there are many different models, one for each Yamanouchi word in this case, and so if I write it like this, then I am saying that okay, I have this left hand side is summation. Now this again, there is an implicit n here, okay, because you saw if we take only, so for example if we take only 2 letters and you take the coplactic class of this, it is not the same as if you take 3 letters and you take the coplactic class of this. In this you would get things like 2, 2, 3. So the coplactic class of this in 3 letters contains this. So I should probably also mention this Bn. Okay, so that's, so Bn is connected component of yam lambda in An star. So the n is hanging around here. So this is W in Bn mu, y mu. So I have some fixed Yamanouchi word of weight mu, and then I have weight of W, then I have some W prime in Bn of y nu, and I have weight of W prime. So I can rewrite this as and then I can just concatenate these words. And the weight of the concatenation is the product of the weights. The way I wrote the weights as monomials. Okay, so what we are looking at is basically, I can write it like this further. Concatenation, which I will denote by a star, is that the notation that was used in the path models? So henceforth the proof is like the same as the path models. So it's just a sum over the concatenation of these two things. Now I claim that this set, this concatenation, is a union of crystals. Which means that it is closed under the operations Fi. Ei, whatever, does not matter, right. crystals. Well, of course, now I can use the word crystals and coplactic classes interchangeably because I have proved that they are the same. But when I say crystals, I mean these crystal operators. When I say coplactic class, I mean the same Yamanouchi word. So why is that? Well, the thing is, suppose you have this word W prime, and you are trying to apply some thing like maybe EI or FI to it, then what will happen is that you would have this one place where you would have so you would have cancelled out all the Ji pairs, and then you would be left with some I raised to R, J raised to S. Of course, these may not be next to each other, but it's certainly the case that so then you will be changing this to I raised to what is it? I'm like totally dyslexic when it comes to this, R plus 1 J raised to S minus 1. So what I want to say is this operation either happens in W or in W prime. Okay, there's a slight difference in the sense the converse is not true. If I have so the thing is there could be a 2 here which gets cancelled out by a 1 here. So they're not exactly the same, but what is certainly true is that if you're applying a crystal operator on the concatenation, then either it's a crystal operator on W or it's a crystal operator on W prime. So this is equal to EIW times W prime or W times EIW prime. But this is enough to show that it is a union of crystals, because now this is in beep n y mu star beep n y mu. Each of these is in. So this is a union of crystals. And now I want to know how many of those crystals, so each of those crystals is going to contribute to me a Schur function, right? Every crystal gives me a Schur function. So I want to know how many crystals will give me the Schur function S lambda. So this is a union of crystals. Huh? Okay, I hand waved actually. Yeah. Huh? I waved my hands. So yeah, maybe it's not difficult. The only issue is that you have 2-1 things which may cancel across the 2 things, but then the point is that the 2's will be in here and the 1's will be in there. So okay, so there's some little argument like that. I think you proved it, right? I mean, yeah, and okay. So then you cannot really. So as Raghavan explained, EIWW prime is either this or this. So yeah. So I want to know how many times a crystal that gives me S lambda occurs in this thing. So this is a union of coplactic classes. But what is the signature of a crystal that contributes S lambda? What is the one key thing that every crystal has? It's the Yamanouchi word, right? So I just need to, if I want to know how many crystals contribute S lambda to this sum here, I just need to know how many Yamanouchi words of weight lambda there are in this concatenation, right? So this is equal to sum over Bn y mu star Bn y nu intersect. So I can write it like this. Okay, so this is a union of Yamanouchi, this is a union of coplactic classes. So each coplactic class corresponds to a Yamanouchi word, right? So what I would say is, let's just look at sum over lambda, sum over y in yam lambda, and then it is the coplactic class of y. W in BNY, weight of W. But this is the Schur function S lambda, right? So what we get is this is equal to sum over lambda, then we have number of Yamanouchi words of shape lambda. So I'll just say cardinality of yam lambda intersect B n y mu star B n y nu times S lambda. Okay, and this n here is, you work with n letters, you will get the actual Littlewood-Richardson coefficient for polynomials of in n variables. So this number is the Littlewood-Richardson coefficient. So let's take that and look at it more closely. So the conclusion of that exercise, and this is the same proof that Littleman, I mean, in some sense Littleman's proof is a generalization of this argument, and the difficulty there lies in the absence of the Plactic monoid. So what is it? It's well, there's still a kind of monoid there. There are all these equivalence classes of paths, but there is no Knuth moves, nothing so simple as Knuth moves to decide whether to, or insertion algorithm to take a path and directly turn it into a tableau. So what we have is C lambda mu nu equals number of W in Bn y mu, W prime in Bn y nu, such that W prime belongs to yam, right? That's what I proved. Yeah, there's some n here. Now the point is, now look at this W prime. This needs to be Yamanouchi, right? Which means that W prime already needs to be Yamanouchi. Every suffix of a Yamanouchi word is Yamanouchi. So what I can take is that I can simplify this as number of W in Bn y mu such that W y nu belongs to yam lambda. Okay, so here this kind of simplifies things quite a bit. Firstly, if W y nu needs to be yam lambda, it also completely tells us, specifies to us the weight of the word W, because sorry, question? No, okay. So, because it also we know the weight of W y nu and we know the weight of the concatenation. So, the weight of this should be the weight of lambda minus the divided by the weight of nu. Let us just look at an example. So, let us start with the simple example, something like let us take mu equals 2 1, nu equals 2 1 and lambda equals 3 2 1. Okay, so now I will take I can take any Yamanouchi word of weight 2 1, right. So, let us take y nu to be 2 1 1. Now, I want to look for W. So, W should belong to B, let us take n equals 3, B3 of, so n equals 3, B3 of y mu. So, let us take B3 of the super standard tableau. Which means that it should be that it should itself be a semi-standard Young tableau of shape 2 comma 1, right. So, this should be a semi-standard, so of A3, but also I know what its weight should be. What needs to be its weight? Well, I have already accounted for 2 of the 1s and 1 of the 2s, right. So, I need one more 1, one more 2 and one more 3. So, the weight of W should be x1, x2, x3. So, W should have 1 1, 1 2 and 1 3, right. So, W can be possible W's, there are only 2 of them, 1 2 3 and 1 3 2, or if you like so let us just put both of them and see what we get. So, what we need to do is now we need to take each of these and see if we concatenate it with this, do we get a Yamanouchi word or not. So, W y nu equals 3 1 2 2 1 1 or 2 1 3 2 1 1. So, are these Yamanouchi? They are both Yamanouchi, right? Yeah. So, two 1 3, 2 1 1. Yeah, they are both Yamanouchi. Yeah. So, somehow in my notes I had concluded this is not Yamanouchi. So, yeah. So, this implies that C 3 2 1 2 1 2 1 is 2 in 3 variables. Let's look at another example. So one of the interesting examples is when you take, so we already seen Peary rule, right, where you just take one of the Schur functions to be a row Schur function or a complete symmetric function, which are the same thing. So what you have to do for that is you need to actually compute all these things. So I think you can definitely have 4 2. Yeah. So if you want all this thing, what you have to do is just concatenate these and look for the Yamanouchi words. So you have only those 8 things over here, and then you see which of them give rise to Yamanouchi words. So you'll always get 4 2, I think. How will you get 4 2? Can you think of a way to get 4 2? So just take 2 1 1 2 1 1. So that's a Yamanouchi word of weight 4 2 in the concatenation of these two crystals. Let's look at an example where now I will not ask for lambda to be, I'll still take nu to be 2 1, and let's take mu to be, let's say, 3, and I won't specify lambda. Okay. So then what do I take? I'll take y nu as before to be 2 1 1. Now mu is 3. So what are all the column reading words of? So I'll take the tableau, the column reading words of semi-standard Young tableau of shape 3. So what are those? They are just these kind of things, right? So you can have 3 3 3. 3 3 2, 3 2 2, 2 2 2, and then similarly you can go down, but then you also have 3 3 1 and so on. So you have all these weakly decreasing sequences. Okay, but I am going to tag it on to this thing here, and so what I am doing is I am just saying that hereafter when I am going from right to left, these numbers need to be increasing. Okay, so I'll just write this like this, and now I'm trying to add more things, and I want the result to still be Yamanouchi. Now remember, if you have a Yamanouchi word and you're doing the column insertion, then always you'll get these tableau of this form, right, with super standard tableau. So now suppose I'm adding these things. So here, for example, I can add 1 3, but then I can no longer add a 3, right, because I have to put at least one more 2 before I can add another 3. So just for example, but it has to be increasing, so so I can't add anything more after this. So this doesn't work. I can't do 3 1 1 this way. Oh, I can, yeah, I can do that, 3 1 1 this way, yeah. I can't add any more 3's, so I can do this. I can in fact add 3 1 2. So what is happening when I do this? So what's happening here is that the weight, how has the weight changed? So I've added a 1 here, I've added a 1 here, a 2 here, and I've added a 3 here. So the way the weight has changed is I have added some numbers to each row. But what I want to say is that I cannot add, so I cannot add, so how many, so the question is how many 3's can I add here? The number of 3's I can add here is the difference between the number of 2's in this part of the word and the number of 3's in this part of the word. The number of 2's I can add here is the difference between the number of 2's here and the number of 1's here. So what I am doing is now Bn y3 consists of weakly decreasing words, and it's completely determined by the weight, by their weight. And so the number of i's that are allowed so number of i's in W cannot exceed there is no restriction on number of ones, but if I start with so let me put it this way. So I want to know what is the difference. Yeah. So you're completely, so for each weight there is a unique word. In particular, these because each of the words I am adding have different weights, these Littlewood-Richardson coefficients have to be 1 or 0, right. So the question is which ones can be 1 and which ones can be 0. So now what I am doing is I am starting with this 1, 2, and then I am going to end up with some other shape, and I am going to add these words, these numbers as I am column inserting them. They are going to give me some 1s, some 2s, some 3s and so on. And what I want to say is that the column insertion is super standard. I want to say that I will not add more than one box to each column. That so for example, if I am adding, I cannot have 2, 2, I cannot have 2, 2, 1, 2, 1, 1. So this would, this is Yamanouchi, right? So 2, 2, 1, 1, 1, 2. Yeah, this is Yamanouchi. So if I do that, then I'll get the shape I'll get is 3, 3, 3, 3. Something is wrong here. Huh? Sorry? I have to look at Yamanouchi words. Oh no, I have to look at Tableau words. Yeah. So I have to look at rows. Oh yeah, that's what I'm doing wrong. Yeah, you're right. So yeah, so I'm doing W in B3 1 1 1. So these are rows. Yeah. Okay. So that simplifies life. So W is a row. So B3 1 1 1 consists of Tableau, which have one row, right? So it's just a weakly increasing sequence, row words of length 3. Oh yeah, now it works well. Now if you have a row word of length 3, then the last letter is the largest, right? So how many times can it have? 3. The number of times it can have 3 is the number of times this has 2 and no more, right? So it can have at most 1, 3. The number of times it can have 2 is the number of times this has 1 minus the number of times this has 2. So in this case it can have at most 1, 2, right? Which means that you cannot add more than one box to each column. So I can have at most 1, 3, right? So let's look at the things which start with 3. So I can have at most 1, 3, so I cannot have any more 3s. But I can have a 2 after that, right? But I can have 2 2s. 3, 2, 1, right? Yeah. And then I can do, okay, then I can do 3, 1, 1. So that takes care of all the 3s. I can also put 1, 2, but I can't put more than 1, 2 because if I put another 2, then there will be 3 2s and 2 1s. Three, 2, 2 is, oh, too many 2s, yeah. So 3, 2, 2 is not allowed. So these are the 3. Now let's look at the weights of these things. So originally I had this thing, and now 2, 1, and now the weight of this is, I am adding one box to each. These are the 3 boxes I have added, 1, 2, 3 for this one. For the second one, I have 1, 1, 3. So I am adding 2 boxes to the first row, and I am adding 1 box to the third row. And for this one, I am adding 2 boxes to the first row, and I am adding 1 box to the second row. Every time I am doing this in such a way that I do not add more than 1 box to this each column. Okay, so you can recover Peary's rule for S lambda times HK using this. So you can try to write a general proof based on this idea that the number of times you can have I in this row should not exceed the difference between the number of i's and I minus I plus 1s and i's in this Yamanouchi word, and which means that you are adding a horizontal strip. Maybe there is a nice way to think of it in terms of abacus and beads also in the same thing. So you should have so much clear space in your abacus. Okay, so similarly you can try to see what happens with columns. I'll give you one more exercise. So take compute C lambda mu nu. Just remember this. And take n equal to 3 again. When mu equals 1, 1, 1, nu equals 4, 4, 1. Let's take n equals 4. So I'll just help you get started with this. So, and lambda, sorry. Mu equal, I should say what lambda is, right? No, that's not the example I wanted to give you. Where is it gone? Ah, here it is. Lambda equals, yeah, this is a nice example I worked out. 4 mu equals 2, 1, nu equals 4, 3, 1, and lambda equals 4, 4, 2, 1. So, and let's take n equals 3. So, at first this may look a little daunting because of the large size of nu, but in fact it turns out to be very easy because y nu you immediately fix. So, it will have 4 ones, then 3 twos, and then 1 3. Then mu has to have shape 2 1, so it is not very big, and you know exactly what its weight should be. Its weight should be the difference between these things, right. So, 4, what is the difference? So, this is the number of ones, so there is no ones, it has 1 2, it has 1 3 and 1 4. Okay, I need n equals 4 here because I have 4 parts there, otherwise I will get 0. Yeah, so it must have shape 2 1 and it must have 1 2, 1 3 and 1 4. So, you have basically 2 3 4 and 2 4 3 like this. So, you have 2 words 4 2 3 and 3 2 4, and then you need to check if they are Yamanouchi or not. So, you see it's quite easy to in practice to work out these things. Okay, so for further reading, as it is, you have this notes by Lascaux, Leclerc and Thibon, but to see different formulations of the Littlewood-Richardson rule in the case of Tableau, I would highly recommend Stanley's book Enumerative Combinatorics volume 2. It has appendix written by Sergei Fomin, and in that you will find a slightly different proof also of the Littlewood-Richardson rule without using the coplactic operations. It uses something called it uses growth rules, Fomin's growth rules, but he also mentions Jardetaken. This proof is an exercise in LLT actually. The proof that they give in LLT is different. Okay, but this is Littleman's proof in some sense. So, this is the proof that Littleman generalized. I do not know where this proof is actually written down properly in the literature, but almost all the steps are given in these notes, the Plactic Monoid by Lascaux, Leclerc and Thibon. All they do not do is the last step which I showed you how to do. So everything, all the technical stuff like coplactic classes are the crystals and the Yamanouchi words and all, that is all there. So the only thing that is left is to finish the argument, and they give it as an exercise. So I will stop with that.